Okay, so this is the first part of section 7.3. These are discs and washers. I may have to do this in two parts because the program that I'm using only allows 15-minute videos, but this is often considered to be the hardest chapter for some kids because you will have trouble visualizing what these things look like. Okay, so here we go. So the disc method is, and you don't have to copy everything down on this slide, and obviously you're not going to be able to copy this drawing down, but here I have a finite number of these discs. They are solid. And then they spin around here, and I would find the volume of each one of these individually, and that would give me an estimate of the volume of that entire shape. Now, if we integrate, just like with rectangles, we could either find the areas using rectangles, or we could use integration. Integration uses an infinite number of rectangles. Okay, so the radius will be in terms of x when we're going around the x-axis. Okay, the height is dx, just like with rectangles. The height was along the x-axis, that is your dx. And this is our general equation if we are going around the x-axis. Because remember, a disk is just a circle and it has thickness. So the pi r squared is the area of our circle, but then we give it some thickness. And remember, it's infinitely thin. So that's going to be caught up with all of the integration. Okay. You don't have to copy this down, but just visualize that shape, that rectangle going around the x-axis. Now, somebody in class pointed out, well, there's going to be error because it goes above this rectangle goes above the graph. Well, remember, these graphs are infinitely skinny, so there's not going to be error. Okay, so picture that going around, and this is what our disk looks like. I will have kids try to plug in numbers for that pi r squared. They'll try to tell me that it is, well, that area is 2. Well, over here, it's not that size, and we're trying to find a general equation. So it would be whatever our f of x is. That's what I would put here. F of x quantity squared, and it's in terms of x. Okay, so write this down. And sketch. And again, the description that they give to these is often the hardest part. I'm going to have some drawings over here in a second, but real quickly, I'm going to put my drawing in the square root of x from 0 to 4. And it says, let's see, the region between the curve y equals the square root of x, 0 to 4, and the x-axis. So we're talking about this region right here. Sometimes it's not as clear as this one. And we're going to revolve that around. I expect to see a mirrored image. And believe me, if you think that I expect you to be artists, that's what I'm drawing. I'm drawing a ham, for those of you who know what ham is. You should always, when you're doing discs and later washers, draw a perpendicular line to the equation you're going, or to the line you're going around. In this case, we're going around the x-axis. Going about the x-axis. And then I recommend giving it thickness. I don't recommend, you should do this. And if you want to, put it over here as well, because what you're doing is you're going to show me the disk. Okay, so that is your disk. It is forming a that's perfectly round. You're using your imagination. And you could have put that anywhere inside. You could have put it over here. And then it gets super crowded and it's hard to tell what I'm doing. So you're putting this disk in, this revolution. If I erase it, it's going to all go away. Okay. And you're going to find this distance, this area here, which is pi r squared times its thickness. So this one's easy. Pi, I will even tell you this. If it's a calculator question, write r squared dx. R equals the square root of x from 0 to 4. If you have all of that and plug it into your calculator, this would not be a calculator question. And with the answer, you will get full credit. And the reason I like when kids do this is on calculator sections, because you then won't get burned for parentheses, because even my best students make stupid mistakes with parentheses. Okay, now over here, I'm going to show you what this will look like. Here we have only 1, 2, 3, 4, 5, 6. 6 of these perfectly round cylinders. You're trying to basically draw one of those for me. That's it. And then here it is getting smaller and smaller. And we're still not there yet. There's still going to be error, but we're getting closer and closer to the actual area over here. And even now this looks smooth, but can you see that we're still going to be having some error up here? And again, no credit, no graph, you're only getting partial credit. You are not getting the full credit. And I've already worked through this entire problem, but again, when I'm going around the x-axis, you should have a perpendicular line. And again, give it some thickness and then try to make it look like a cylinder. Not a cylinder, I'm sorry, I'm a disc. Okay, I've already done this one with you. And there's our answer. Okay, so what if you have to go around something other than the x-axis? Pause as you need to write things down. So I'm changing this question. Now I have the square root of x, the line y equals 1, and the line x equals 4. So this shape right here is here. This is not going from x is 0 to x equals 4 anymore. And I need to show that I'm setting the square root of x equal to 1. That happens when x equals 1. So my shape is going from 1 to 4. I'm still using pi r squared dx. Now this drawing is not going to be to scale by any stretch of the imagination because this thing is actually all above the x-axis. But so that you can see this, I draw my perpendicular lines. I put some thickness to my disc in there. My radius is not the square root of x. It is this distance right here, which we talked about in section 7.2, how to find that distance. My radius in this case is the top equation minus the bottom equation. This is the square root of x. This is 1. And we're spinning that thing around. And if I plug this in for my radius, square it, that will give me the volume that this crazy shape is making. And again, same thing. I want you to see what this looks like. And this time I have 7 pi over 6. Next. So now we have to talk about vertical revolutions. So instead of using x values as our limits of integration, we're going to use y values. We're still using pi r squared. And again, I always put my pi out in front because it's a constant. So our first example with this will be, again, pause so you can get this written down. Okay, so for me, I'm looking at this. I have no idea what this graph looks like. I'm not going to rewrite this in any way. There are always dangers. You are probably not going to be able to rewrite most of them. I know when y is 1, x is 1. So here I am at 1, 1. This is 1, this is 1. And then when y is 4, x is 1/2. So up here, I'm like this. So this graph actually comes down with like a little arch right here. And I am revolving this shape around the y-axis this time. So I try to mirror that on this side. I'm working with the original shape over here, and I'm going to draw the perpendicular line, the line that to the equation I'm going around, which in this case is the y-axis. It is x is 0. And I'm going to mirror that over here, give it some thickness. I did these much better on paper, believe it or not. So this time my disc looks like this. Again, I'm using pi r squared, this time dy. Along the y-axis, I'm going from 1 to 4. My radius is just the equation. Just like if I were to find, if I were talking about y equals x squared, this distance right here is x squared. From the x-axis to the equation, that's f of x. From the y-axis to the equation, that's f of y. So f of y is 1 over the square root of y. And I do that work. This would be a by hand problem. This would not be a calculator question. Now, if this were a free response question, once you make that 0, your answer pi, ln 4, you're good. But the problem is a lot of times these are on the multiple choice. So you're expected to know that you could rewrite this as 2 pi ln 2. Here we go. So this shape right now, I purposely picked this one because below this line right here, it's a solid. We would use disks from 0 to whatever that is. And then from this point to this point, I would use the washer method. I would have to use the disk method twice because I'm actually trying to get this hole eliminated in the center. And this one's around the y-axis for whatever reason, but we're going around the x-axis first. So whenever we're rotating something, if the shape doesn't border the axis I'm going around, that means you have to use the washer method. And the equation is just the disk method twice. And again, on the AP test, I would prefer you have r squared minus r squared with parentheses dx from your first x value to your second x value. Okay, try to picture this going around the x-axis. Okay, I'm not going to be able to deal with this timing. And it looks like it's almost like a flower petal. And then this one going around the y-axis. This one, the same shape going around the y-axis, is actually making a bigger flower petal. Just because it's the same shape, if I tell you to go around the x-axis and the y-axis, does not mean you're going to get the same value. Okay, so make sure, don't just make that assumption. That is not a guarantee. Here is what a washer looks like for those of you who do any kind of home improvements, help your parents with anything. Anytime you put a screw in something, you use a washer because that gives it a tighter fit. Okay, y equals x squared plus 1, and y equals negative x plus 3. I am going to revolve this around the x-axis. So I'm supposed to emulate that down here as well. Nothing but luck. Okay, we're going to pretend that's the same. And I'm using the original shape. I'm going around the x-axis, so I'm doing this. I'm going to draw a perpendicular line. You have to have that perpendicular line. I'm going to give it some thickness. I'm going to do the same thing over here. Pretend they're the same. And then I'm going to draw 2 washers, or 2 discs rather, I'm sorry. Okay, so that is our washer. Looks like, oops. Hello. It looks like this with thickness. Okay, we have to find our limits of integration, which means I need to set x squared plus 1 equal to negative x plus 3. X squared plus x minus 2 equals 0. And I get x minus 2 or plus 2, x minus 1 equals 0. So x equals negative 2 and 1. These are our limits of integration. We're going from negative 2 to 1. Okay, everything's going to go away. Stop. Okay, then